So, Mark, we have a very good understanding now of how the helix turntables deal with resonance that's coming from the environment, usually up the stand,
Yeah.
and up to 100 hertz. How do we deal with resonance above 100 hertz without giving away any of your trade secrets? Because I'm fully aware of the amount of work and research that's gone into what happens beyond there. But how do you, in principle, deal with anything above 100 hertz?
We talk about constrained layers
Mm-hmm.
and effectively a multiple layered sandwich of materials that each layer is designed to do a particular task. So in engineering terms, you can use a thing called finite element analysis, where you throw a mesh of triangles across a shape.
Yes.
And then you put the material properties that you can define from manufacturer's sources. So it's Young's modulus, the stress strain curve, the coefficient of expansion of the material, the typical damping behaviour of that material, what we call damping factor.
Yeah.
And damping factors can be engineered in. For instance, if we were using a cast iron material, the reason why a lot of internal combustion engines were cast iron blocks from many, many years ago was the cast iron actually absorbs vibration very, very effectively. It's an excellent damping material.
Yeah.
And it's low cost.
Yes.
And so they could make lots and lots of them. The issue with that is its damping factor goes up to about 10, as it were. Then as you go up into some of the more exotic alloys, you get into the copper alloys, copper manganese, sonostones, those sorts of things, often used in the marine world. Propellers that need to not ring.
Yeah.
So in case you want to hide yourself from underwater.
Submarines and
submarines,
things like
etc. So those materials can be blended, and you can get up to a factor of about 30. And then above that, you get into what they call hydamets, high damping mets, materials or metals. Then you start to blend alloys of magnesium or aluminium with zinc and zirconium, grain refiners, to pull the lattice structure of the metal closer and closer together to create more grain boundaries, which means that when the material is flexing, those grain boundaries, there's more of them to rub against each other, which creates a shear force in those boundaries, which creates heat, like you're rubbing your hands together to create heat. They dissipate a lot of energy. They can go up to a factor of 60.
Yeah, wow.
And in the frequency ranges that they work, they typically, you choose the materials for the vibration problem.
Yeah, that you have.
That you want to damp.
Correct.
And so by listening with accelerometers and acoustical means, you can determine what the problem frequency is, and then you choose the material to apply to that problem frequency as close as possible to the source of that. And the idea is to prevent that source of noise bleeding across to the next most critical component.
Yeah, okay. So being with you on this journey for the last few years, I think my way of explaining it to people would be that you have used metal composition or metallurgy combined with Fibonacci style sequences, or not quite, but similar.
Not quite, but yeah.
To identify a particular frequency of resonance that's above 100 hertz that exists in the chassis, and then chaperone it away from the critical areas.
Okay,
of the turntable.
That's shape optimization,
Mm-hmm.
and that is knowing that, for instance, a cymbal, a music cymbal,
Damping and shape
you
optimization.
you can hammer that cymbal and create stress in a
Yes.
particular area, so that when the drumstick hits that cymbal, the vibration spreads evenly around the surface of the metal, and you'll see hand-beaten cymbals worth way more than just something that's spun.
Yeah.
And
Mm-hmm.
they have their own unique tones that are very carefully crafted by the artisan, the hand-beaten gongs and cymbals and those sorts of things. In engineering terms, we can use those same principles of deforming a metal in a particular region. It raises the stress, which creates a pressure zone, so that when vibration travels across that, it's going to change its behaviour. And you can analyse materials now with X-ray crystallography, where you can see inside the materials to highlight what we call the von Mises stresses in the material. And that is validating what you've calculated. So the software used to predict the modes is really good. And if you then get it validated with something as fancy as X-ray crystallography, or measured with, in our case, laser interferometry, which is not uncommon now in loudspeaker designers are using these tools to measure the vibration across the surface and create heat maps of where the problem areas are. And that was, as an engineer and designer, you think this is what you want to do, and it's only when you actually check it that you go, it's behaving like we predicted it would, or like the software. The idea is to get the software up to the level where the measured and the predicted are so close that you've got confidence then to do the next stage.
Yes.
So we've engineered that into a series of stacked laminations, constrained layer, and we are steering vibration into what I call buckets. The buckets are where it can sit and it doesn't bother anybody.
Yeah.
You don't want it in the arm.
Yeah. For example.
You don't want it in your bearing, if at all possible, and you're trying not to let the motor generate its noise into the bearing or the arm board, but you also don't want noise getting back into the motor to re-amplify.
Absolutely. Now that brings us to the next stage in this thought process, which is that we've really covered the resonance and vibrational energy that's coming from the environment. However, a lot of resonance is created within the internal systems of the turntable. Predominantly the motor
and the bearing.
Yeah. So
and the arm.
And the arm as well. Yeah. Absolutely. So tell us a little bit about how you have gone about isolating or managing those sources of resonance which are sitting in the middle of your system.
So each one has a different frequency. This thing in the middle is spinning at 33 or 45. That generates some natural frequencies. In the case of 33 RPM, it's 0.55. But that's not the problem frequency. The bearing surface, which you're trying to skin with oil as the material that's rolling between the oil molecules are rolling between the two metal surfaces. You have a thrust pad typically where a lot of pressure is being put on a small ball point of some description, and the thrust pad is a hard material typically, or it can be a sacrificial material, but they grind, and that noise is audible, and it is at a higher order.
Yes.
It's almost in the vocal range, and you need to address that noise by damping.
Right.
You can't float the bearing magically in air. Some turntables use a magnetic pressure relief, and that's a very valid way of addressing the amount of pressure on the bearing. if you don't have a grounding point where it doesn't settle on a hard surface, that creates a magnetic spring.
Yeah.
And then the platter's bouncing all the time. So to avoid that, magnetic bearing designers will try to have at least a touchdown point on the bearing. The issue then is that to get a contiguous magnetic material that is perfectly magnetized,
perfect flux density, everything.
Flux density, BL curves or BH curves, across the rotational surface, nigh on impossible.
Yeah.
So you're going to get portions of the rotation where it's easier and portions of the rotation where it's not as easy in the per rotation. So you're creating a problem in doing that.
Yeah.
I decided not to use magnetic relief in this bearing design, which meant not placing 80 kilos or 40 kilos of load on the bearing point. So you can play with the platter masses, knowing that they affect the processional mass. Remember, it's all interrelating.
Everything is a sequence of
events.
Compromises of different challenges.
So what we call the grinding noise of the bearing, which is inherent in all bearings, okay? All bearings do it to a greater or lesser degree, trying to prevent that noise from reaching the arm and trying to prevent it from bleeding back into the motor. The motor itself also is a spinning device. Now, if I put that motor in the centre and it made a direct drive, it lowers some of those noises significantly because it's very slow. But you can then create another form of noise, which is modulating the way the platter rotates. That's a noise.
Yes.
If I have a faster spinning motor that's separated from the bearing and I'm coupling it either by a rim drive or a belt, then I've got bearing noise in that motor that can bleed into the system. So the idea is to prevent it from getting into the bearing and preventing it from getting into the arm.
Yeah.
So those stacked laminate plates, the shape, optimization, and the way they're positioned in relation to each other, whilst maintaining geometrical rigidity between the 2 points. So on the Z plane, which is height-wise, we have on an X and Y coordinate, we have no movement between the motor bearing and the turntable bearing. That reduces yawing.
The yawing motion
effects. If we were to separate that motor out and put it off to the side here
on the table.
On the table, people say, oh, well, then you've decoupled the motor. But no, the motor doesn't float in space.
It's connected
to the table, which is connected to the turntable.
Yes.
It might create a more tortuous path for the vibration to get back into the system, but you lose control because you can't guarantee what it's been placed on. So in this case, we're controlling very tightly the relationship between the motor noise and the bearing noise. We've got full control over what this does. As technology improves, the motor can be changed out for new motors and you've still got the same relationship. So it's actually...
it's almost geometric.
Yeah. And then the choice of belt then becomes another device which you use to reduce the interference.
Do you have the motor and the bearing arm on different planes?
They're on the same plane from the horizontal.
Yes.
So what I would call the Z axis. They are at different heights, but in an X and Y location, they are geometrically fixed with each other.
Okay.
So I want them on the same plane to prevent yaw, which is a classic suspension problem.
Yeah, absolutely.
If your motor is separated from your suspension system, you will have yaw. Now, yaw, the only reason it's a problem is because there's a thing called Young's modulus. And Young's modulus is, if I was to use, say, this ruler as an example, if I was to push the ruler out over the edge here, you see that do that. If I keep pushing it out, you'll see the ruler start to drop. That's where the weight of the material is overcoming the internal strength of the material, the stress strain curve. So, and then you've got an undamped oscillation at the end of it. So if you have a system with a suspension build up to the limits of its spring, it will then release that overshoot and correct, and we'll constantly be doing this movement between the two devices, which leads to anomalies in the rotational performance,
which is audible,
and we're trying to reduce those. Ultimately, in a perfect world, you would have none of that movement, and that's one of the reasons why direct drive came to the fore, is because it could reduce that yaw, but then it created an rotational vibration of a higher order,
sort of cogging,
which led to a brightening of the sound. So everything that you do in this system has a concomitant effect on something else. It's a challenging system to control.
Must drive you crazy.
It does actually. It doesn't keep me up at night, but it does cause me to think about things when I should be thinking about others, or doing something. So
it's such a fascinating thing, because a little micro environment full of resonance landscapes everywhere, and you're trying to go to all this effort, all this technology, all this research, to simply isolate that moment where the stylus is in the groove of a record.
It's the
so
groove.
You can sit back and close your eyes and
George,
and get lost in the music.
That's why we do it.
It's a
but
silly
the
pursuit.
The more you learn, the more you realise what you don't know.
That's right.
This thing has, and that's why I think it's such a vibrant and healthy market, where other innovators around the globe are also looking at the same problem and trying to come up with solutions. And I love that part of the turntablism and why, looking at the work other companies are doing and admiring it, there's a lot of room for improvement. Continuously. So so far we haven't run out of things to do.
Well, just imagine, not that long ago you were involved in a previous turntable design that you created, and that was state of the art for its time. And just in that time between that turntable and now, how much technology
has
become available to you that you never could have dreamed?
Well, apart from the miniaturization aspect, which helps when you're doing things. The current vacuum project that we're working on, something that was yay big is now this size. It's incredible. That helps. But also the sensitive measuring equipment has increased in capability and scale. The software's got so much better for us to see what's happening and also forecast and predict. So I think we can still absorb that from industry to find out. And then there's materials science, the constant release of new materials. We haven't covered it now, but the clamp tech, the material science that went into that wasn't available to us.
Absolutely.
5-6 years ago.
And not to mention AI, artificial intelligence. We've gone beyond that.
Go on.
We have MI, Mark's intelligence. It's serving us okay at this point in time. But I think AI will have a big role to play in the coming years as well.
I think just from doing
some of the complex calculations of resonance. Because resonance is very complicated.
You can see that in the aviation industry. And also that it's changing the shape of objects. They're becoming more sinewy. It's almost like somebody's opened up and peeled back the outer layers, and you see all the musculature structure. Formula One, the suspension arms don't almost look alien-like now because these are mimicking nature in more effective ways.
Absolutely.
And I think that aspect of bone-like, sinew-like shape changes being driven by AI and software is the new frontier.
And isn't it ironic that all this computing and intelligence power is effectively creating shapes that exist in nature?
Yeah.
And nature worked it out a long time ago.
Worked it out. Well, there
Anyway.
was a greater intelligence involved, I might say.
Good discussion, Mark.
So, yeah.
Thank you very much.
All right, George.
Good on you.
Thanks.